So this resumes part 2 of this video series with 4th grade geometry. We do have a task 7 that has 3 different standards, 4G1, 4G2, and 4G3. And so that will comprise of multiple ideas of drawing points, lines, segments, looking at different angles, parallel, perpendicular, looking at two-dimensional figures, recognizing symmetry and whatnot. But I gave you 4 examples, and we're going to draw those. So I would, if you have not already, cut out the protractor that I have given to you in your notes, and it should be at the end of your homework as well. If you haven't done that, I would ask you to go ahead and stop the video and cut out or print out. There's 2 protractor examples that I gave you. I don't care which one you use, it's fine. Just if you don't have your own protractor, I did provide one that you could use as a paper copy. Now, I'm going to give you, and also if you would have a centimeter ruler nearby, I'm going to also give you some directions on how you can draw. So definitely use the measurements that I give you to help you with drawing some of these triangles. Well, if we're going to draw a right and an isosceles, what I would ask you to do is draw a line segment that is, let's say, 4.5 centimeters. And then I want you to draw another line segment that's 4.5 centimeters. And when you connect those two, I would want you to measure that. And you should be about 6 2/10 centimeters. Now this is a 90 degree. And if you take your protractor and set your, the middle part of your protractor, and I want you to measure what this angle measure would be, you would see that that would be 45 degrees and this would be 45 degrees. So since the two angles are the same, that would imply that the 2 lengths are the same, which we know they are because I asked you to draw 2 segments that are the same. So this would be a right isosceles and identifying with your right angle. Next, let's look at an obtuse scalene. So I would ask you to take your centimeter ruler and draw a segment that is 2.5 centimeters. And this vertex right here, I'd like for you to create a 129 degree angle. So it looks something like this. So that would be 129 degrees. And this should be 5 centimeters. So you would want to go ahead and create that segment that would be 5 centimeters. And then you would connect your other line and its line segment, and it should be 7 centimeters. This angle measure right here should be about 16 degrees, and this one should be about 35 degrees. So what does that give you? It gives you 129 and 16 and 35. So when you add all those up, you're going to get 180, which is how much, it's your degree measure, the sum of the angles in a triangle. The next one, I want you to, and by the way, let me back up because I don't believe I highlighted this, but this would be your obtuse angle. And why is it scaling? Well, it's scaling because this segment was 2.5. This segment was 7 centimeters, and this segment was 5 centimeters. So you have 3 different side lengths, 3 different angle measures, which describe the attributes of a scaling. And what's in purple is the 129 degrees, which is larger than 90. So there's your obtuse. On this third one, I want you to draw an acute scaling. So we're going to draw a line segment and label it 3 2/10 centimeters. And I would like for you to create an 82-degree angle measure here and a 45-degree angle measure here. So this will connect here, and that should be 3 9/10 centimeters. And this will be 2 8/10 centimeters. So on the third one here, I want acute scaling. Well, this should be 53 degrees. Here has 45 degrees, and here you have the 82. So 82, 53, and 45 gives you the 180. It's scaling, remember, because you've got 2 8/10, you got 3 2/10, and you've got 3 9/10. 3 different side lengths, 3 different angles. And when you have that, you've got your scaling. Now look, 82, 53, and 45, they're all acute. Last one, I want an acute isosceles. So just go ahead and take a segment here, and that will be 2.5. I'd like for you to draw a segment that's 2.5 centimeters. And then I want you to draw 2 segments that are 3 8/10 centimeters. That should create a 70-degree angle, and this should be a 40-degree angle. So notice here you've got 3 8/10 and 3 8/10, so there's 2 that are the same. You've got a third one that's not the same. You have a third angle that is different, but you have 2 angles that are the same. And that's going to create your isosceles, because isosceles should have 2 angle measures and 2 side lengths that are the same. And why is it acute? Because you have 1, 2, 3 angles that are less than 90 degrees. Number 2 in this task, question 2, says draw all the possible lines of symmetry that you would have in the triangles above. And there's only two triangles that would have symmetry. It's the last one that we drew. It would have your line of symmetry here. And the first one that we drew, the right isosceles, as it goes through the vertex. So remember that some triangles do not have lines of symmetry. And it's probably because, as you see, their sides are different, their lengths are different. And if the sides are different, then there's no way to be able to match up those sides when you try to draw the symmetry line. There's no way to fold it and it be identical. So just continuing with this, with task 7, we have question 3. It says, are the following statements true or false? So I want you to be able to explain using pictures or using words. And In this case, I'm just going to verbally say it, so I won't take the time to write it down. And you can rewind the video if you need to write this down for your own notes. But for number 3, is triangle ABC an equilateral? If triangle ABC is an equilateral, then segment BC must be 2. True or false? Well, this is a false statement. Why? Well, if triangle ABC is equilateral, what does that tell you about all the sides? That all the sides should be the same. They should have the same length. So that means that segment AB, if segment AB and AC are equal to 1, then what should segment BC equal? Well, it should also be 1. If we look at part B here, we say a triangle cannot have one obtuse angle and one right angle. True or false? A triangle cannot have one obtuse and one right angle. Well, that's true. So think about how you could draw that. Well, if you have one right angle and another has to be obtuse, well, they're never going to connect, and that is make a triangle. You're going to end up having a quadrilateral. So a triangle cannot have one obtuse angle and one right angle. So there's no way to connect the 3 line segments. They're just not going to meet. Part C says triangle EFG is described as a right triangle and an isosceles triangle. True or false? Well, this is a true statement because the tick marks represent that the side lengths would be the same, and then you notice you have a right angle. So angle EGF is a right angle, and an isosceles triangle has 2 sides of the same length, and you're seeing that in segment EG and GF. Part D says an equilateral triangle is isosceles. True or false? So with this one here, you just need to be careful with the wording, because when you're talking about an equilateral triangle, we're saying that all the sides are the same length. But when you're talking about an isosceles, and then you're looking at 2 of the sides are the same length. So you may have to look at the word, exactly. So when we're saying exactly, an isosceles triangle has exactly 2 line segments that are the same. And an equilateral triangle would have exactly 3 line segments that are the same. So with the wording, we'd have to say false if we're looking at using the word exactly. Finally, if we know that triangle HIJ, and we say that angle A is equal to angle B, is this true or false? Well, we have to look at the triangle again, and we see the tick marks represent that this would be an isosceles. So remember some of the isosceles triangles that we've drawn already. If this was 40 and this was 40, then that would be 80. So that means this other one would have to be 100. Or we could look at another one. We could say this is 70 and 70 and 40. So if it is, if A does equal B in this triangle, we can certainly fold it. This is going to be a true statement. Our line of symmetry would be here. And like I was saying, if this was 70 degrees, then this would be 70 degrees, and then this would be 40 degrees. So we could fold this triangle along its line of symmetry to show that angle IHJ is equal to angle IJH. And that concludes task 7. So looking at task 8, we're going to do some more constructing. So notice the standards, G1, G2, G3. It's all going to involve two-dimensional figures, thinking about lines of symmetry, thinking about parallel, perpendicular lines. So that's what those 3 standards together highlight. So construct figures. Let's look at the first one. Construct quadrilaterals with at least one set of parallel sides. Well, we could look at a trapezoid, and that's going to have one set of parallel sides. So at least one set of parallel sides we could say is a trapezoid. And we could look at another type of trapezoid. And we see the parallel sides as well. And then we can think of at least one set of parallel sides, so we could look at a parallelogram. We can look at a rectangle and a square. So those would be quadrilaterals with at least one set of parallel sides. And based on earlier drawings, we could even say a rhombus. Part B, let's construct a quadrilateral with 2 sets of parallel sides. And 2 sets of parallel sides can be the parallelogram. So you see the 2 sets of parallel sides, so that would be the umbrella term would be parallelogram, which has the rhombus and the square and the rectangle. Construct a parallelogram with 4 right angles. Well, that could be four right angles, could be a rectangle. Could be a square. And a rhombus. Those would all be parallelograms with 4 right angles. And then finally, construct a rectangle with all sides that are the same length. And a rectangle with all sides of the same length, remember that can be, that's not a great square, but that's what I'm trying to draw. And if it has all right angles, it could be a square, and which is the same as a rectangle, which is the same as a rhombus. Remember, a square contains all of those characteristics. So that concludes task 8. No, it doesn't. There's a part 2 to that. So we're going to use the word bank to name each of the shapes. So in part A, notice we've got parallel lines, just one set. So this would be your trapezoid. Part B would be your parallelogram. D would be your rectangle. And C would be your square. Question 3 says, explain the attributes that make a square a special rectangle. So I'm just going to kind of speak some of the characteristics, and then you can write those in your notes, rewind the video if you need to. But a square is a special rectangle. Why? Because each of its sides are the same length, instead of just the opposite sides being the same length. So a square, like a rectangle, has 4 right angles. So those are some attributes that make the square a special rectangle. Number 4, explain the attributes that make a rectangle a special parallelogram. Well, a rectangle is special because it has 4 right angles. So you think about the square and the rectangle, they both have 4 right angles. And a rectangle is a special parallelogram. And then the last one, explain the attributes that make a parallelogram. And in this case, parallelogram is not really a special trapezoid. My wording is off there. A trapezoid, that's just a bad question. So think about a trapezoid. Trapezoid has exactly 1 pair of parallel sides. And when we think about a special quadrilateral, a trapezoid can be and is a special quadrilateral because it has 1 pair of parallel sides. And we can look at, we could even call this an isosceles trapezoid. And here's just another version of the trapezoid, but you can see it has the 1 set of parallel lines, and then this one has the 1 set of parallel lines. So that concludes task 8. So we're going to look at task 9. And notice we come back to a couple different 4th grade standards. So we're looking at measurement and data for MD5. So now we're going to recognize angles. We're going to think about a reference to a circle. We're going to think about the 360 degrees, and one angle is 1/360th of a degree. And we want to think about turns in regard to angles. So in this case, we're just going to look at benchmark angles. So I always want you to make a list of the measures of benchmark angles. So if we're starting with, let's say set A, I'm going to start with 45 and use 45 as the benchmark angle. So 45, 90, 135, 180, 225, 270, 315, and then we'll stop at 360, which was an entire turn, 1 rotation. Let's look at set B. And with set B, we started out with 30, and we're going to use 30 as a benchmark angle and basically skip count by 30s. So 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 360. So we look at all these degrees. Now, question 2 says circle any of the angle measures that appear in both lists, and then what do you notice about those? So let's go back to the list here, and what are in both lists? Okay, I see 90 and 90, 180 and 180, 270, 270, 360, and 360. So those are angles that are in both lists. And question 3 says, question 2 said circle them, but then what do you notice about them? Well, we would say that they're all quarter turns. And they're all right angles. So if you think about the circle and think about the 45 and then the 180 to the 270 to the 360. So if you think about the quarter turns within a circle, you've got your 90 and then another 90. So you're looking at all of these here, which are all right angles. Question 3 says, list the angle measures from this problem that are acute. So the only ones that are acute would be the 45, the 30, the 60. So those are the only ones that are less than 90 degrees. And then number 4 says, list the angle measures that are obtuse. So in another color, let's look at the ones that are obtuse. And that would be 120, that would be 135, that would be 150. So those are obtuse because they are larger than 90, but then less than 180. Question 5 says, all right, well, if we realized in our work today that 1 degree is equivalent to 1 out of 360 degrees of a whole turn, so it's 1 out of 360. That means that 2 degree angle is 2 out of 360. So what fraction turn of each of the benchmark angles? So let's look at these as fraction amounts, okay? So set A. We had 45 out of 360, 90 out of 360, 135, 180, 225, 270, 315, and then the 360. So all of these, notice the fraction is out of the total, which is 360 degrees. And then we can do the same for set B. And you can refer back to the list. We had 30 out of 360. I'll skip around. We had 120 out of 360. Well, we had 30 out of 360, 60 out of 360, 90 out of 360, 120 out of 360, 180. Or 150, 180, we had 210 out of 360, we had 240, 270 out of 360, we had 300, we had 330 out of 360, and then of course we ended with 360 out of 360, which is equal to 1, which is that entire turn. So you think about how many 30-degree angles does it make for a full turn? So when you think about, when you go back and look at our list, how many did you have that involved a turn of 30 degrees? And you had 12. So it says, how many 30-degree angles does it make to make a full turn? And that would be 12 30-degree angles. This one says how many 45-degree angles? And that would be 8 45-degree angles for the full turn. And then the 12 30-degree angles. And then so if you didn't have a protractor, you think about how you could reconstruct a quarter of it from 0 to 90. Well, you can use two 45-degree angles. So you could use two 45-degree angles. You could use three 30-degree angles and put those together to make that right angle template. So that concludes task 9. So we've got 2 more tasks to look at. So task 10 is going to be more of constructing angles given the number of degrees. So if I want to draw a 30-degree angle, then I want to think about using the protractor to do that. And so I would set the middle of my protractor here, and then I would measure. One way to do is to measure this way, so you can create that 30-degree. So this is what we'll talk about this in later grades as well, but that's your initial side, and then here's your terminal side. So that terminal side is just moving from 0 here, kind of right to left, that's creating that angle measure. So that would be 30. And then if I wanted 170, and I may have to put, if I wanted 170 degrees, I have to change my line segment just a little bit. So if I came up here, well, that's not true. I can, if I want 170, well, I know what a straight angle is. The straight angle is 180. So I may have to start kind of in this middle part here and then just show that that's just that 10 degrees remaining. So from right to left, I've created 170 degrees, with this being 0 and this being 180, that straight line. With 115 degrees, I would do the same thing. I'd let this be the middle of my protractor, and then I know that that should be 90, and 115 degrees, well, 10, so another 25 degrees here. So what you're doing is you're just creating, if this is 0, you're creating that 125 degrees, knowing that that's 90. And if I need to get to 115, 10 to get to 100, and then 15 more, so that'd be 25 degrees beyond the 90 degrees to give me 125. Or 115, sorry, not 125. And then if I want to draw a 65 degree, I can go the other way. I could make this be 0. And then draw my angle from left to right, and show that angle measure of 65 degrees. So those are just approximations using the protractor. And you can see additional videos that will be uploaded as additional practice, just some links that you can look at that I'll embed that will talk to you through how you correctly use the protractor. And some of you probably already know how to do that, so it's just kind of a refresher. But you can look at the protractor in a couple of different ways. And when you're thinking of it by looking like this, you can start here and let this be 0 and work your way this way. So some protractors are going to have one set of numbers that'll go to 180 degrees, but then you also see another 0 over here that will work its way over here to go to 180. So it's really just kind of which way do you want to look at it. And so that concludes task number 10. And so then task 11, we're looking at 4MD7. And that is looking at measures that are additive. So we're going to look at angles that we can decompose into non-overlapping parts where we know what the sum of the angles would be. So we're thinking about, in this case, we know that angle GFE is a right angle. So if we know this is a right angle, then that means, well, what does that mean? We know that one angle I don't know. One angle is 20, and the sum is 90 because I was told it was a right angle. So this X would have to be 70. So we're composing angle X and 20 to give us the 90 degrees. And on part B, I know that IJK is a straight angle, and a straight angle we know is 180 degrees. So that's telling me that X plus the 70 is 180. So that's got to be 110. I can count up or I can subtract. 180 minus 70 would give me 110, or I can count up from 70, 30 to get me 100, 80 to get me to 180, so 80 and 30 would give me 110. Here's another example where I'm giving you that angle QRS is a straight angle. So I know all of this is 180 degrees. So I know that this is 90. I know that this is X, and I know that this is 36. And it should all equal 180 degrees. So if I combine these two, I'm going to get 126 degrees plus X, and that would give me 180. And so with 126, if I add up, I'm at 4 gets me to 130, and then 50 gives me to 180. So X would have to be 54. So that would just say that 90 plus 54 plus 36, all of that should add to 180 degrees, which is the straight angle. And then finally, another way to look at this, I also know that angle ZYV, so ZYV is another straight angle. So all of this is 180 degrees. So I know that 60 degrees plus 108 degrees plus X degrees should be 180. So this should be 168 degrees plus X. And if I count up from 168, so 2 degrees will get me to 170, 10 will get me to 180, so X has to be 12 degrees. So that just means that 60, 108, and 12 all added up would give me 180 degrees. So that concludes part 2 of this video series for 4th grade, looking at the geometry standards, 4G, 4.G.1, 4G2, 4G3, 4MD5, 4MD6, and 4MD7.